friends, and welcome to our third of our virtual field trips in our soil and water conservation series. These are produced by the University of Arkansas Division of Agriculture through funding from the NRCS and also with their collaboration. NRCS is the National Conservation Research Service, our resource service. My name is Mike Daniels, and I'm an Extension Soil and Water Conservation Specialist for the University of Arkansas Division of Agriculture's Cooperative Extension Service. And I want to thank all of you for joining us today. I think you're going to find this is going to be an exceptional program, and we're going to learn a lot about sustainability and conservation, especially in rice, and how we can become more efficient with carbon and nitrogen. And so before we get started again, I want to thank the USDA Natural Resources for their funding. And I just want to turn it over here in a minute to a couple of my colleagues, but I am honored to be sitting here with two of our experts in the field on this area. They're world-renowned, Dr. Ben Runkle. He's a university professor of biological and ag engineering. And then he's brought one of his Ph.D. students, Will Richardson, who's doing a lot of really exceptional research in the area under Ben's leadership. So I do want to thank both of you. How you doing, Ben?
Yeah, very good. Thanks for having us.
Yourself?
Doing well. Happy to be here.
Well, good to have y'all here. Like I said, Ben is a professor of biological ag engineering, but I'm going to turn it over to Ben, let him tell you a little bit about himself, and then he's going to talk a little bit about what he's doing in this area in terms of his research.
Yeah,
Ben,
sure.
take it away.
Yeah, sure. So I've been a professor at the University of Arkansas for about 11 years. I arrived in 2014, and I've been focusing my research activities on the integrated carbon and water cycles, and I've really focused my attention on sustainable rice production practices, doing a lot of quantification in farmers' fields. We'll hear more about that in the video. I also have a teaching appointment, so I also teach some classes, both undergraduate, graduate classes, and I do some mentoring of graduate students.
Super.
Yeah, hello, my name is Ben Runkle. I'm a professor of biological and agricultural engineering at the University of Arkansas. We're standing here in Jonesboro outside of a research station co-run by my colleague Michelle Riva at the U.S. Department of Agriculture's Agricultural Research Service. It is great to have partnership across the state with people like Michelle Riva, with the farmers who host our research, and with the countless others who contribute their ideas, insights, and resources to our research program. My group works to quantify the benefits and challenges associated with transitioning to sustainable rice production systems. We mostly focus on farm pre-harvest research, and we're investigating questions associated with water use, greenhouse gas dynamics, grain quality, optimizing field operations. As an engineer, one of the things that I recognize in farmers and also in the plants is that we're all engineers. The farmers are trying to optimize on short and long time frames. They're thinking about today, tomorrow, and years from now, all concurrently, and sometimes that causes challenges. And likewise, the rice plants are trying to optimize, where do we put our carbon today? Do we put it in the grain? Do we put it in the root? Do we build our defenses against different challenges? And sometimes we need help to get that right. And so my group is here to help quantify the impacts of different practices. How much water can a farmer save? When do we need to try to do more with less? And when do we need to try to do more with more? You know, sometimes we need more inputs, sometimes we need less inputs, or we could get by with fewer inputs and may reduce the input costs and still increase the output costs or different things. And so we're working with farmers on real farms. It's often challenging. These are really big fields. There's a lot of heterogeneity in the soils and in the way the rice is planted, and that can cause challenges from a scientific perspective, but it provides us the value of being able to say our work was done on working farms. We have built our measurements across these difficult conditions, and that can help scale the results more quickly. The work that we do is at different scales. We have team members looking at really microdynamics within the soil or within individual plants or plant leaves to better understand photosynthesis, root allocation, water use dynamics on a plant scale. Then we also harvest the grain and get an understanding of the impacts of on-farm practices on the yield or on the grain quality in a number of different metrics. We're also using approaches to measure the greenhouse gas dynamics and fertilizer use on plot scale, so maybe something from a couple square feet to a couple, maybe 10 square feet. And then we also have instrumentation like what you see behind me in the picture that is micrometeorological. It's like a weather station on steroids, we say. And that is looking at greenhouse gas dynamics across the whole field. We have really sensitive instrumentation that provides a really high quality read on how much greenhouse gas emissions from the field are, how much carbon dioxide the plants are taking up in photosynthesis. And that really helps provide an integrated signal of what's going on at the field level. And that data is really useful. It's really challenging to collect, and so there's not a lot of these stations around the world, but when we have that information from rice systems, we can link into people doing different types of modeling, of forecasting. How will the rice respond to different weather events? How will it respond to different fertilizer strategies or irrigation regimes? And by building our confidence from the small scale to the medium scale to the field scale, we can help deliver kind of more sound research findings, quantified estimates so that they can be built into conservation practices and programs. Our aim is that we could help unlock financing for farmers to be able to get better insurance rates or reduced input costs or conservation benefits from the consumer who wants to pay more for kind of green goods, or for supply chain companies who want to work on sustainability in their operation, and that some of that profit could go back to the farmer. None of those programs can work if there's no data underlying them. People need to know what they're paying for and need to know just how much we can reduce the environmental impacts or promote the growth of the rice in different circumstances. And so we're out there measuring. We're measuring in different soil conditions, in different irrigation strategies, across different seasons with different weather conditions, in different parts of the state which have different amounts of sunshine and wind and temperature conditions, earlier, later planting dates, and so on. And our aim is to build an integrated picture of how all of those different practices interact to create a productive and healthy rice production system that's also sustainable and boosts some of the conservation and stewardship goals that we all share. Changing to more sustainable operations or implementing different conservation practices, that can be quite challenging because we're asking farmers to change a part of their practice, and they often share with me, changing this practice here means that later in the season I have to do something different, and then next year I have to do something different, and our field is meant to deliver water in this way and not that way, and so I recognize it's quite challenging. And so some of the conservation strategies like alternate wetting and drying or multiple inlet rice irrigation or furrow irrigation, they're not necessarily for everyone. I think everybody needs to evaluate what is the right solution for your farm and where can you make a difference. And for some people, that might mean raising the boards a little bit at the end of the during the season so that you can store more rainfall on your field so there's less runoff. For some farmers, it might mean implementing a tailwater recovery system. For some farmers, it might be doing one mid-season drainage and not multiple drainages through the summer. And all of those things have benefit. One of the things that our research allows us to do is to quantify incremental benefits of those different practices and hopefully still deliver some conservation benefits that we can, by quantifying that, we pave the path for future reimbursement or compensation or incentive programs that can help facilitate those kinds of changes. Farmers know their land really well, and they know what's best for them. Like the engineers that they are and that I am, we're all looking at different time frames of analysis and different degrees of risk and uncertainty. And so my hope is that by doing these careful measurements of greenhouse gas dynamics, that also includes water vapor, we're also measuring evapotranspiration, we can help deliver real insights to the farmer about when are implementing these practices most important and when can you kind of back off the implementation of the conservation practices to prioritize the yield producing practices. When is it best to fertilize? When is it best to keep water on the field to sustain a healthy rice crop? When should you start considering other concerns like pests and fungicides and those other considerations? Farming is a really integrated and complex system, and our work is aimed to deliver on that. Some of the research that we're doing on alternate wetting and drying is looking at the methane emissions associated with rice production. Many people may have heard of methane gas. It's a greenhouse gas. It's also what's in natural gas. It's what we burn in our stovetops. But methane is produced in rice fields because it's produced under swampy soil conditions. So the kind of flooded conditions quickly use up the dissolved oxygen in the water. And the microbes then convert the organic matter into methane, which is a greenhouse gas. It's a loss of organic matter, and it hurts our atmosphere. And so the alternate wetting and drying, by re-oxygenating, draining the field, re-oxygenating the soil, can help really minimize the methane that's produced. We have field scale work that shows just one drainage event can reduce the methane emissions from that field by 40%, and 2 or more can reduce the methane emissions by up to 80%. And they can often be done without impacting the yield, without that much extra work on the farmer's part. It takes a little bit more monitoring. You don't want to get the field too dry. But often it allows the farmer also to use less water. They can pump less, so they're saving energy costs. They're using less water, so it helps replenish the aquifers. They can capture rainfall, so they're able to take advantage of that kind of periodic free gift that we get from the sky. And it provides some other benefits. The rice plants are unique as plants that they can grow in those flooded conditions, but they don't have to. They're also quite happy to grow under not flooded conditions. The oxygen can reach the roots faster, and they can grow quite healthy in those circumstances. So there's a lot of potential, we say, co-benefits or multiple good outcomes that can happen from 1 or 2 drainage events. Our work also shows that the longer the flooded period, the more methane is produced. So the goal would be, the task or request would be to reduce the methane emissions by simply breaking up that flooded period. If you can change an 80-day flood duration to 2 40-day durations, it really makes a big impact in terms of reducing the methane emissions. There are other strategies that can be done for sustainability in terms of thinking about how to optimize the planting schedule to take advantage of rain or surface water resources, to think about ways to build surface water reservoirs or take advantage of some of the surface water flows so that we use less of the groundwater in an area. We also need healthy rice to be able to produce more grain on the same amount of land with the same amount of water. And so I also am looking to work with colleagues in genetics and breeding to think about optimal rice production strategies, rice that can survive drought or dry conditions and harsher weather conditions, to think about different production styles that can be more efficient at producing even more grain on the same land, because we all do need to eat, but we want to do that in a way that's respectful and conserving of the resources that are given to us. We enjoy working with farmers on farms, and we always learn a lot from working with the farmers, and it seems like they're learning from us as well. So some of the farmers that we're working with say, we were really suspicious of this program and this idea when we first started. Doing alternate wetting and drying is not something that our parents did or our grandparents did, and the way that our farm works, it's not necessarily for us, but we gave it a shot. And many of them are now implementing so many dry down events during the season. They're really making an impact in their water use and in the methane emissions. And sometimes we even call them to make sure that they're putting enough water on the field themselves. So I would encourage farmers to just give it a shot. Just try to do a dry down event on one of your fields and see how it works. See how it feels to get that little boost of rice growth, and test for yourself whether you're reducing the water use, whether you're reducing the electric bills a little bit or the gas required to pump that water out. And then look around for some of the sustainability programs that exist. There are private sector and public sector programs that encourage this kind of irrigation management that could be an opportunity for you. I'll talk now about how the instruments work behind me, and this is quite cool. So come with me as my engineer kind of science geek moment. We're measuring the greenhouse gas dynamics over these fields, and that is carbon dioxide, what the plants breathe in and then breathe out as respiration. We're also measuring the methane emissions coming from the field. Methane is 2 parts per million in the atmosphere. So if you take 1 million pieces of air, just 2 of those are methane. So I was thinking about, in the US, we have 300 million people. If we have the same ratio of methane in the air as people, we would have 600 people out of that 300 million are methane molecules. So we're measuring greenhouse gas dynamics using this instrumentation that's measuring the methane concentration, the carbon dioxide concentration, the water vapor concentration in the air, and they measure it 20 times per second. And so that actually captures the turbulent movement of those gases from the surface to the atmosphere or from the atmosphere to the surface. So every moment we're measuring the breathing in of carbon dioxide as photosynthesis, the breathing out from the landscape of water vapor as evapotranspiration, carbon dioxide as respiration from the plants in the soil, and also the methane gases that come off of the surface from the microbes in the soil. And so we're really measuring the breathing of the landscape. So again, we're measuring the concentrations 20 times per second because we want to capture the turbulent movement of those gases to the atmosphere. And we're measuring it 365 days a year. And so we're able to also look at a whole seasonal perspective, a multi-annual cycle. We're looking at how do weather conditions today impact the gas dynamics tomorrow. There's implications of that for the methane emissions that we've talked about, but also in understanding plant photosynthesis. How do rice plants, which are really well accustomed to wet conditions, how do they do during a dry down? So far, we're not seeing too much of an impact. They're really able to survive. They have roots that are deep enough to tap the soil moisture, that they're able to survive well. They're not suffering a loss in photosynthesis or a change in some of the other metrics that we're able to measure. And so that's really good news. The rice is adaptable and amenable to some of those drying conditions. And that facilitates testing even further, drying a little bit more, using a little bit less water, maybe waiting a day or two to apply the water, draining a little bit earlier. All of those strategies can make a real impact in terms of the total water that we're withdrawing from our aquifers. The evapotranspiration measurements that we're doing can also help facilitate an understanding on a regional level of how much water does rice need or do other crops need. We can put that into different databases. We can use satellite information, weather station data to deliver big scale predictions of how much water is used here, how much carbon the landscapes can store, what might happen to the soil organic matter under different treatment conditions if you have different residue management or burning or some of the other practices that are performed here. When my team is out collecting the data, the data is logged because it's so much information. We're logging 20 times per second, all of this information. We need to come out here. It's logged to a USB stick, and then we're collecting it. We do have an internet-enabled interface, so we're able to log in from our offices and check on how the instruments are doing. What is being logged, how dirty and clean the sensors are. That's also something we can check on. It's a dusty environment in agriculture, and so our team does have to come clean some of the mirrors in these sensors. The sensors work by looking at how much gas molecules are in the air, and the more of the methane that's in the air, the less light is absorbed in this kind of headspace that we're measuring. And so there's some cleaning that needs to be done in the mirrors on a kind of weekly basis. That also allows my team to come out and take notes about how the field is doing. We're doing measurements of the canopy height, the stage of the rice, the depth of the water. We're checking on some of the other instruments that we have out here. We have wind, air temperature, humidity, radiation conditions. Also in the soil, we have soil moisture, soil temperature conditions, so that we can put all of that information together in our models to better understand the greenhouse gas dynamics, the water use of the plants, and the rates of photosynthesis. We're also doing stuff like measuring what is the leaf area index, how many leaves are there in the field over a given area. That's a helpful indicator of the plant growth dynamics. That's also something that we can tie to the satellite information. So every day we have satellites from NASA and other places that are monitoring our Earth's surface, and we're able to use that information to predict yield in advance of the harvest. We can give that information to farmers about, this is a time when your field should be greener than it is. Maybe it's time to do some more fertilization or make a change in your irrigation strategy. There's a lot of really nice ways to tie information that we collect here on the ground to information that can be useful to many others across the state, the region, or even the world. Some of our data has been used in studies that are looking at rice globally in Asia and Africa and other places. So it's a really powerful set of instrumentation and measurements. We've had support for these measurements from a lot of different places. We've had support from the US government, the National Science Foundation, the US Department of Agriculture, the US Geological Survey, also the private sector. Some private companies are really interested in the sustainability of their supply chain, and they're eager to be able to convey those savings in quantifiable terms, and they need people like us out there measuring the benefits in the field, so that they can recommend to farmers with confidence that we want you to do these practices because it will deliver these benefits. And then it goes in their annual sustainability reporting, what they're doing. And so the suite of funders is really helpful. It also provides us with different perspectives. They all have slightly different needs and goals and aims. And so our research can bridge some of those different things. We can draw connections between people who really are interested in carbon cycle science or climate science with yield, with water use and sustainability in that area, grain quality metrics, with farmer livelihood as an indicator. When we tie all of those things together, then we can really deliver a more holistic perspective on best practices for farming, for quantifying some of the benefits and challenges associated with that rice production. Some of our work on the farm really depends on the coordination of the collaboration with the farmers, with all of our researchers, and we're always really grateful for the support of the farmers and the funders that have supported us and the colleagues and collaborators that come to our research site and perform additional measurements. We're really building up a great data set and a story of how to be more sustainable. The alternate wetting and drying and some of the other irrigation practices we measure have the possibility to save water, save energy, reduce greenhouse gas emissions, and either promote or be yield neutral. And so it's a really powerful opportunities for farmers to make a difference and for the green consumer, for companies interested in sustainability to incentivize that. I think there's some really great opportunities here for the future of agriculture and rice production in Arkansas and even globally.
Hey, Ben, this was great information, really well done, but I know it's going to prompt some questions from our audience. And audience members, if you want to ask Ben a question, you just type your question in the chat, and then at the end of this webinar, we'll be able to bring up some of those questions and get the answers. But one thing I noticed from watching this is that Ben used the term sustainability quite a bit. Sustainability in my mind is just the continual improvement in this case, with efficiency. We can't control what prices are going to be. So we can't always help farmers with the prices, but we can help them with efficiency. And I noticed that, carbon and nitrogen cycle in the soil, and they can be lost through gas. The problem is, until you showed up, and Michelle Riva, and then another one of our colleagues, Dr. Chris Bry, we really didn't know how to quantify that. So that part of the cycling, nitrogen and carbon cycling, we didn't have numbers for, so we didn't know how much we were losing. And I just wanted you to talk a little bit about how much is your research starting to give us an understanding of, can we someday change our practices to be more efficient with our nutrients and reduce inputs?
Yeah, sure. That's a great question and a great conceptualization of sustainability. I think there's no such thing as sustainable. It's a pathway. It's something we all want to get to, and maybe for different reasons and different metrics. And the metrics that we're thinking about today are often this carbon and water and nitrogen cycling. And that means, trying to do more with less and to lose less of what you put onto the field. And so, we have the opportunity to build up soil health and with soil organic matter and residue returns to the soil. But if some of that is lost, either as CO2 or methane, or as nitrous oxide on the nitrogen side, those are losses for soil fertility. And then they're also bad for other parts of the environment. If it's downstream as nitrate, that's a water pollutant. If it's up in the air as nitrous oxide, that's an air pollutant in terms of greenhouse gases or climate change. So all of these things are integrated, and we need to think carefully about it. But fortunately, we think that we have now more and more data to bring to the table so that it's hard to change farming practices. They are streamlined, farmers have a lot on their mind. And so the aim that we have is, how do we provide enough evidence to make subtle shifts to some of our practices? And that could be the exact timing of some of the fertilizer, the style of irrigation, how to manage that well. That can really add up to something impactful.
Yeah, and Ben, another point you brought out is you're building data sets, and we do that with Discovery Farms on water. And I think the important thing about that is, if you think about, we can't measure the type of measurements you're making everywhere. Although I think someday we'll see more and more of this being done routinely. But it's just like weather, predicting the weather. We can't make weather measurements everywhere. But if we can make enough of them that we get confidence that we can repeat that and predict it with models, And I think the same thing is going on with your research. We have to have this baseline information. It's critical for us to have a better understanding and then maybe be able to predict where we can't always measure. Would you comment on that just a little bit?
That's absolutely true. In the same way that our weather forecasts have improved from a 5-day to a 10-day forecast, we're hoping to do the same with a lot of other carbon dioxide metrics, predicting photosynthesis rates, which ties into a good prediction of your yield further and further in advance when there's still time to make an impact in the field. So our data has been used for that. It's also useful for irrigation scheduling and planning, and that's of course a critical part of farm management and aquifer use. So, a lot of that, and it's all driven by data. We have to be out in the field collecting all this information and then helping synthesize it so that other smart researchers and companies can take it and develop interesting products with it.
Well, I'm certainly encouraged by how this works, how critical it is to helping farmers in the future. If we don't have this information, we don't know how to manipulate it and use it to the profitability and the betterment of our farmers in farm situations. So I also think I want the audience to understand that if you're a young person and you're thinking about a career and you think farming's not high tech,
there's a lot of
you're
high
wrong.
tech. Yeah, that's right.
I mean, when you look at what Ben's doing with the flux towers out there, it doesn't get any more high tech than any field you're in. But we need to shift gears because we got another guest here. Ben, we really appreciate that. And you'll have a chance to ask questions at the end. But we also have one of his students, a Ph.D. student, getting closer and closer to graduating, Mr. Will Richardson. And he's going to talk a little bit about this technology and what they're doing in the lab. And before we do that, Will, tell us a little bit about yourself and why you have interest in this and what is it like to work for Dr. Runkle?
Sure, yeah. So I'm originally from Little Rock. I did my bachelor's also at the U of A in biological engineering. Went elsewhere to do a master's, and I'm back. But yeah, a lot of my post-undergrad research has been in agriculture and specifically now in rice. And that kind of all stems for me from growing up as someone who had grandparents that were farmers and saw how important it was to our livelihoods as humans. And when I was deciding what I want to do with my life, I was like, well, we always have to eat, and I want our world to be, a healthier place for all of us. So it seems like the best spot for me to be in. And within Dr. Runkle's group, my focus is more on the photosynthesis side of things. So he was talking a lot about the breathing of a landscape, plants taking up CO2, and they have to do that to be able to grow and also to eventually produce grain. So like you mentioned, we can't put one of these flux towers on every single field. But as far as photosynthesis goes, it's not just about that CO2 exchange, but that's all driven by how plants interact with light. So how much light are they absorbing from the sun? That's used to drive that photosynthesis machinery within those plants. And so my role of that is sort of measuring how plants absorb and reflect that light, both at the ground scale next to our flux towers, and basically connecting that so we can see what can we learn about how light is reflected and how that is connected to photosynthesis. And so we can take those measurements, do the exact same thing that we do on the ground, but from satellites that NASA and other agencies have up there, and hopefully extend our ability to monitor photosynthesis from one field with this expensive equipment to many fields with freely available data.
Okay. I think we're going to see a video here of you in the lab. We're going to go to the lab and see what you do there in the lab.
Yep.
So one of the ways that we measure the environmental impact of agriculture in rice fields specifically is to measure emissions of environmental gases like carbon dioxide, methane, and nitrous oxide. And while we do that in one way with our eddy covariance towers, one of the methods that allows us to get many more samples across various rice fields and within rice fields to assess variability within fields. We can make measurements with these chamber systems. So right here we have a portable gas analyzer. And what we'll do is take this can measure, this one measures CO2, but we also have some that measure methane and nitrous oxide. And what we can do is we put a set of collars in the soil around the plants, and then we can sample the gases going into and out of that little soil plant water setting with one of these chambers. So we can place this chamber directly on top of a collar. It makes an airtight seal, and for something like either 3 or 5 minutes, air will be sampled from inside of this headspace in the chamber, sent to this portable analyzer about 1 time per second. And from that, we can get an estimate of the flux of methane, nitrous oxide, any other gas of interest to a researcher or to a farmer in many places inside of a field. And so we tend to do that at least once a week in the rice fields to get sort of a comprehensive understanding of how irrigation management and other management factors affect the amount of gases coming into or out of this sort of land atmosphere system. Sometimes at the beginning and sometimes at the end, we'll take measurements of soil characteristics as well. So kind of like I talked about with variability within fields, the same goes for the soil profile. So on a soil survey map, you might see that a field only has one or two different series of soils in the field. But oftentimes there are more fine nuances to the differences in texture and material of these soils. So here we've got a soil sample that we usually sample the soils before and after the growing season. And so one of the really important things about soils is that they can all hold water in different ways. So for example, a soil with much more clay versus silt or sand would really hold on to that water and allow the rice plants to access it for longer, whereas the silt loam or have more sand, it's not going to hold that water quite as well. And so that's important for our understanding of how to manage fields as well as the environmental impact of different water management strategies. Also, at the end of the growing season, we take samples of grain from various points in these fields, both to measure what's called a harvest index, or basically how much of a rice plant's biomass is put into the grains versus other stems and leaves over time. And so what you can see right here is that we have unmilled rice. So this is rice that you would harvest from the field and has not been milled yet. But we basically look at this to get an idea of how yield varies within the field as well. So here we have one of the gas analyzers that we use for our eddy covariance method of measuring emissions of these different gases in our fields. And so kind of different from the chamber method where you have to go there, close the chamber, wait for 5 minutes and then to get your measurement. We have these instruments set up, these gas analyzers, along with what's called a sonic anemometer, which measures the wind speed in all three directions, 20 times per second, each of these. And we can basically look at how the vertical wind speed and the concentration of the gases within these analyzers that are measured, how those co-vary over time, which gives us an estimate of fluxes of carbon dioxide, methane, and also water vapor. So we can measure plant photosynthetic activity as well as soil respiration by measuring CO2. We can measure methane emissions, and we can also measure the amount of water vapor that's evaporating from the field, or what's called evapotranspiration. And so sort of how these instruments work, we've got within these mirrors right here, there's a laser that's tuned to a very specific wavelength that in this case methane strongly absorbs. So based on how much of that signal between these two parts of the sensor, how much of that signal gets sort of diminished is related to how much methane is in that parcel of air that's being sampled by the gas analyzer. And so one of the things we check both remotely and while we're in the field to make sure that we're getting good measurements is things in the field happen. Everything unexpected always happens. And so whether that's a bird deciding to land on the sensor and to maybe leave some of its waste on one of the mirrors, or a lot of dew that's formed overnight that settles on the mirrors, we might see this signal, the strength of it go down a lot. And so we have to then clean the mirrors with something like a lens wipe to go ahead and get the signal good again. And so that's just kind of what we do. We'll clean this bottom mirror as well as the top mirror. And it should generally increase the strength of the signal. You can see that this mirror also spins, and so while we're in the field, we actually have a washer system that hooks onto one of these parts of the sensor, and the washer will just put some water on the mirror, we'll spin it around to help get it clean. And so, yeah, this is our Lightcore 7700, which measures methane emissions. We can actually see what this instrument is measuring in real time, and we do that with our Lightcore software. So here you can see that I've got an interface that shows the different sensors we use. So this one right here is the one for methane. This one is for CO2 and water vapor. And we can choose any of those variables to plot so that in real time we can see, one, if the instruments are measuring realistic values, and also just to kind of get an idea of what's happening in the field. So you can see that in this current case for an instrument that's out in a rice field, we see the CO2 concentration is kind of between 420 parts per million, which we would expect. It's kind of a realistic value for the ambient CO2 concentration. And so sort of through this too, we can check on our data storage allocation so we can see how much data we have on our USBs that log the data, which we will then take out from the field, plug into a computer, copy it over just like you would, as well as we have a unit that does real-time processing so we can get flux values sort of every day. And sort of part of that is we have an automated daily report that comes out, and so this is one from yesterday, I believe. And so we also have some digital cameras in the field so we can see basically what the crop looks like every day of the year. And you can actually see in this one that there are some weeds that are close to our tower, which is unfortunate, but that's kind of another part of it. And so on this graph, we have just sort of easy diagnostics to make sure that everything is kind of going okay in the field. And we can kind of see the real-time effects of water management on some of these either emissions or uptake of certain gases. And so, for example, here's just a plot of voltage at the tower, so how much power we have. We can kind of see if there's been any spikes or might be any damage to equipment in that way. This plot right here is the signal strength. So when I was talking about the mirror being dirty and needing to be cleaned, we can see that in this plot right here. If these ones get a little bit too low, we know we need to clean it to get it back up. And then we have other emissions or fluxes of different quantities here. So we have evapotranspiration as one example, methane, as well as CO2. And we also get other real-time information like the ambient air temperature right here, the wind speed, how fast the wind is blowing, and then wind direction. And so we make our measurements on the north side of these fields because it's a production field. We can't get out into the middle of the field. And so we try to take advantage of the fact that often our winds come from the south. That's where we make our measurements. And in addition to complement our measurements of emissions, we're not just trying to understand how much of a certain gas is coming into or going out of a field. We also want to know why, in terms of what's driving our measurements in terms of weather conditions, as well as farmer management practices. And so to kind of help put everything into context to really understand the measurements holistically, we use these data loggers that can be connected with sensors that measure air temperature, relative humidity, incoming solar radiation, as well as things like the water level, so we can get a real-time measurement of how much a rice field is flooded, as well as the soil moisture status. And so we've got another thing called a multiplexer that can basically vastly expand the number of channels that we can measure in on the data logger. And so those are happening it's measuring data probably once every minute, storing averages and other statistics on a half-hourly time scale. So we have our weather and soil conditions data perfectly synced up with our flux data. And so every time we go to the field and to collect data from these sensors and clean them, we'll basically just pull this open and pop out a flash card. And then just like any other compact flash card, you can just stick it into a card reader, into a computer, copy that data, and then put the card just right back in. So these are a few of the measurement techniques and methods we use to monitor rice fields in Arkansas.
Wow, Will, that's really fascinating stuff. And I got to tell you, I was a student at the University of Arkansas as an undergraduate 40 years ago. I can't believe it's been that long. But we were trying to do some of the same measurements, but we didn't have all this technology and all this, and it was difficult to even get one data point. Can you talk a little bit about the technology in terms of how does that excite you, and do you think that all this monitoring technology we have, will it be used more routinely by those that serve agriculture and farmers themselves?
I do hope that it will continue to become more of a commonly used thing for both farmers and scientists. Speaking of the data points, in some ways, it's almost an overwhelming amount of data. We're almost at the entire opposite end of the spectrum, and so even moving to the point where we often work in things like spreadsheets, but sometimes a spreadsheet isn't even good enough anymore. I've got to write a computer code to be able to plot and analyze these data points, and so it's really exciting. I think it takes us a lot of time to really not just scratch the surface of what these data mean, but really dive into it and be able to tell a whole story. And I think even something as simple as more distributed weather stations can really help with that monitoring. Can I set up a cheap weather station at a farmer's house and use that to give them an estimate of how much evapotranspiration is coming off their field, or something like that? So I do have hope that things will be more and more adopted, especially as technologies continue to become more widely available and more affordable and accessible.
Okay. I think you have a unique perspective. I want you to share with our audience based on your background. We have trouble attracting students to agriculture these days because a lot of students don't grow up on farms. Yet there's still a major need for workers in agriculture, and they don't have to have a farm background. Would you talk about, give some students or some potential students, what you enjoy about it and how much technology you're exposed to and why agriculture?
Yeah, so honestly, one of the things I like the most about working in agriculture is that I'm not always working at a desk. I mean, and sometimes we're, in harsher field conditions in the summer. It's hot, it's humid, there's bugs. But an advisor once told me that if you really want to be outstanding in your field, you need to spend some time standing out in your field and really getting to know it. And so I find that really valuable, talking to farmers and getting a real perspective on what matters to them, what they're willing to do, what they would never do. I think that's really interesting. And as far as getting into agriculture itself, I would just encourage people also to think about how important it is for us to be eating healthy and balanced meals every day. And, that's one of the most critical things for everything in our society. And so I would say that agriculture is really a place where really humanity kind of meets up with these larger needs in science. And so it's a cool intersection to be able to study problems that are complex, but also incredibly important for humanity. And that can even start with something as simple as just asking a farmer, what kind of problems they're dealing with, what they would like to see happen, just trying to get involved. So I would definitely encourage all young people to kind of ask some questions, see what it's like.
I really appreciate that. And I do think young people, you need to understand there are going to be some good careers in doing soil and water conservation monitoring and this type of stuff. But getting back to your program, Ben, and your research, this is just outstanding. It's critical for our farmers. I'm so excited that you do this. I've admired y'all's work from a distance. And I think it's going to be critical to the future of our farmers in a lot of different ways. We've got a lot of questions. That's not surprising, but let me throw some of these questions at you for the remainder of the time that we have. Ben, this one's for you. Do you feel that row crop rice is overall more sustainable versus water-drenched rice? Row crop will require herbicides. Will this increase the overall sustainability?
This is a great question. I think we must have a very smart audience. Row rice, I'll briefly explain, is irrigating rice in rows like you would irrigate corn or soybeans. And it's been adopted by up to 20% of rice farmers in Arkansas over the last 10 years. It's had a really quick up and coming nature. And it can be water saving, and it is certainly labor saving. A lot of farmers are willing to take even a small yield loss to do it because they don't have to build as many levees on their field, and that is labor intensive and sometimes physically challenging work. And so it's attractive in a lot of ways. There's evidence that it can save a lot of water, but we have done some experiments with farmers where it's actually used more water, because if the soil conditions aren't quite right, you end up pouring more water down the slope. The question is about herbicide, because in the kind of upslope area of the field, you have drier conditions that are more susceptible to weeds. How do you define sustainability? I think Will, Mike, me, and the audience members will all define it a little bit differently. It depends on how much we weight these different metrics. So if you care really about herbicides and chemical pollution, maybe this isn't as sustainable for you. But when you put all those different things together, water savings, greenhouse gas dynamics, fertilizer use, yield, farmer livelihood and physical well-being, and herbicide in context, we're all going to weigh those things a little bit differently. I think there's a lot of potential. Given its rapid rate of adoption, I'd say that there's some sustainability there. Farmers really want to do things that make sense for them, and that makes sense. So let's keep pursuing it. It does need more research. We need to figure it out a little bit more.
Right. Hey, another question is how much savings is possible with alternative wetting and drying?
Yeah, alternate wetting and drying can reduce water use by 20 to 40%, which is pretty cool. And I want to also have the audience think about why that is. When you don't have water on the field and it rains, you get to keep that water. It's like a free water. If your field is already full of water and it rains, it runs off. In general, when you have less water on the field, you have less runoff, less percolation, less open water evaporation. So when you're reducing all of those losses and you're increasing the potential for the gain of rainwater, then you can really reduce your water use. And on the methane side, you're reducing methane emissions by 40 to 80%. So there's some pretty strong environmental benefits of doing alternate wetting and drying. Maybe I also add that in some countries, a mid-season drainage is a standard practice because it helps invigorate the roots. And so there are also real agronomic reasons to drain the field once or twice during the growing season.
Ben, I think you hit on a great point. Some of these conservation practices have dual or even multiple benefits in different areas. And I think that's critical that, and we don't always understand that yet, and we don't even always know that, but your research will help us better understand that some of these benefits aren't just in one direction. They may be for a lot of variety of benefits derived from that.
That's right.
So, let's ask Will here a question. With the photosynthesis monitoring, it happens in two main wavelengths, but what do you see as a real difference from field to field on these wavelength absorptions?
It's a good question. This instrumentation is pretty expensive, and so it's hard to put a lot of these sort of spectrally resolved monitoring systems on many fields, but I would say at least within the growing season, you can really see as the plants grow that in those red and blue wavelengths, which are primarily the colors of light that plants mostly absorb. Our eyes see plants as green, and you can see that there is a tiny bit of a green bump where they don't absorb quite as much of that green light. But oftentimes, some of that spectral information may be impacted by cultivar or disease, and so we've not really looked at any of those so far, but there is a lot of potential to do that, as well as expanding that to the satellite scale to see what the big differences are. But as well as the absorption capacity in that red and blue, a lot of the differences as well come in this what's called the near infrared, or just what's slightly beyond what our eyes see in the red. And so a healthy plant typically reflects very strongly in the near infrared. They have no use for that light, and so we can actually look at that reflectance metric to see sort of how much photosynthesis the plants are doing.
Okay, and Ben, back to you. A lot of farmers may want to know this. How well tested are some of the different sustainability practices, and are they safe to do on their farm, and will they be profitable?
Those are big questions. So we're doing our best, and we have a lot of collaborators who are also helping out to quantify these different things. It's really tough to quantify these on all types of farms. We have lots of different types of soil, land use histories, farm management techniques, machinery, cultivars, or varieties of rice. And so we try to do stuff and think about how to make it adaptable or go beyond the impact of where exactly it's measured. So I would say some of the techniques, the biogeochemistry related to methane emissions, nitrous oxide, those are pretty well studied. How to actually implement them in different circumstances is a little bit more complex. We're dealing with real people, water flowing across kind of dispersed landscapes in these farms. That becomes a little bit more challenging. So yeah, there's kind of a range of understanding that's out there. So I would also look to where is the Conservation Service incentivizing these programs? They're not going to incentivize something if they don't know it's going to work. And so, the government has done their job and their homework and collected stories and studies from people like us, and the things that they're recommending and paying for are well tested, and they're paying for things like, they call it intermittent irrigation. That's the same as alternate wetting and drying, and some of the other management techniques, reservoir building, and some of those things are also good conservation activities. And so those things are well studied, and they're also things that can become profitable, either from the direct payment from the government or private sector programs, but also by reducing input costs and maintaining a high and healthy yield. It's also, profit is one metric of economic success. They can also open doors in terms of reducing the cost of insurance or reducing the risk or the long-term risk on a farm. If you're conserving your resources, that farm is still going to be around for a couple more years or a couple more generations even.
Yeah, I have that same view, share that same view about NRCS, and that their conservation practices are well tested, but we don't know how well they perform. We don't quantify the performance, and I think your research is helping us quantify the performance of how well they work.
Yeah, that's right. Yeah, so, right, and maybe just to expand on that point, the conservation service says, do this practice or don't do it, and here's a payment or not. And our work is to kind of flesh that out a little bit. And that's especially important for unlocking private finance. So companies want to be able to say, we saved this many gallons of water. It can't just be a lot or a little. It needs to be a certain number. And same for the greenhouse gas reductions or soil health metrics and stuff like that. And so the work we're doing is helping to reduce that uncertainty. The more we reduce that uncertainty, the more confident they are in incentivizing it. So it all kind of comes together there.
Right, and if we ever go to market-based incentivization where companies will pay a better premium, quantification will be important for setting those market values.
That's right. Yeah, they don't want to just know that you did it. They need to know that it made a positive output or outcome as well. Yeah.
This is a question for Will. What does a typical trip to the field and field work look like for a Ph.D. student?
Yeah, well, it starts early, whether it's doing some travel the day before or even early in the morning on the day that you plan to do that work. So we're based out of Fayetteville, but our main field sites are somewhere between Lone Oak and Stuttgart. So it takes a while, but I usually come down the night before. I'm fortunate that my parents live in Little Rock, so I can stay with them, have a nice home-cooked meal, get up very early in the morning, probably before the sun comes up the next day, bring a lot of water, head out there, be prepared for a long day and for anything to happen. But a lot of the main tasks are exactly what I kind of showed in that video. I want to make sure all of our sensors are working okay, that we're getting good data, make sure that everything's clean, that no animals have, kind of run amok at the site or, anything like that. And then in addition to that, we'll be making these regular measurements every week of canopy height, leaf area index that Dr. Runkle talked about, which is sort of how much square area or area of leaf there is per ground, which is a great indicator of how the crop is progressing and how it's doing, as well as measuring things like water level to make sure our water level sensors that are automated are, kind of reading the real thing. So that's kind of a typical day. Yeah.
Yeah, and I think it's interesting that you guys work in rice, because Arkansas is the leading producer of rice in the nation. We produce over 50% of the rice grown in the United States, and so we need to play a role in helping them become more sustainable. But one thing that's really impressed me about your work, Dr. Runkle, is your willingness to go out and partner directly with farmers and include them in the process. Can you talk a little bit more about how that's been of value to you?
Yeah, sure. Well, it's great. They're very smart people, and they're very generous, and they let us onto their land and onto their operations, and they share their ideas, their resources that we've borrowed, their side-by-sides and other stuff to get out into the field. And it's really important for us to be able to demonstrate that these practices work on real farms. I think that when somebody's going to try something and they hear, oh, you did that in a greenhouse, show me on a real property. And if we bring that data to the field, to the table, a lot more people are going to take that up and can demonstrate that it works. The field is also where things happen, and so we need to be there. It's what the satellites can see and give us information about. It's where people are making decisions, and it's also where sustainability claims are made. When you buy a package of something that says it's well produced, they are looking at field scale metrics, so it's important for us to be measuring at the field scale. Right, absolutely.
I think that's so important to help provide perspective for researchers and to improve our relationship with farmers. Here's a question. I think that's kind of interesting because being involved in this type of work, I know it's very, very expensive. It's not cheap. How much does money does it cost to put one of these multiplex or not a multiplex, but one of these flux tower.
Yeah, the flux towers with measuring methane and everything is $100,000 of instrumentation, and really, that's a lot of money. Of course, it's also a lot of money to pay for the people to maintain them and to interpret the data and to understand them, and to drive down to the field every week. A couple hour drive really adds up when you're paying for those miles. And all of those costs, though, to me are worth it, and they're also shared by these different interests. So as I said in the video, we have had support from the National Science Foundation, the NRCS, the other parts of the U.S. Department of Agriculture, the U.S. Geological Survey, who cares about water resources, dynamics, and then also the private sector. And so all of those different people have brought different resources to the table and have contributed something. Of course, the farmers have also given us a lot. So to me, it is valuable. And what's also especially important is that we translate what we're finding from this very expensive instrumentation into a way that's legible and translatable for people. We can't put those everywhere. And so how do we transmit the information in a way that's still rigorous and adaptable so that farmers can make wise decisions for their farms?
Yeah, somebody wanted to know, are you getting funding from NASA?
I am, yeah. So NASA is interesting. Of course, we know NASA is a space agency, and we care a lot about that. It's so neat to know where we are in the universe. But NASA also owns and operates a lot of satellites that are Earth observing. And so they're helping understand Earth is a planet, and Earth is where we live. And so they have all of these imagers, and they take pictures of things, and we can translate how green an image is to how rigorous is the photosynthesis, what are the carbon dynamics like there, and we can even now work on early detection of stress. Sometimes you see it in the greenness in a way that you might not be able to tell from just driving by or looking at your field, so that we can implement changes to farm practice in time to keep those yields high.
Okay, we got time for maybe one more question, and this one's directed to Will. What are some projects and research topics that you're most excited to pursue in the next 5 years?
Yeah, that's a great question. So I'd say one of the next big topics for me is basically taking what I'm finding at the field scale with these field measurements of how plants interact with light, that's coupled to those eddy covariance measurements of the CO2, and basically try to expand that out to more fields. So our satellites can see many different fields, and so trying to connect that to really do more regional scale monitoring of both rice and other crops as well. And then kind of along with that, Dr. Runkle's been working at the U of A since 2014, and so we've now got about 10 growing seasons of data of all these fluxes. And so between all of those 10 years, we have really quite a wide variation in terms of whether there was alternate wetting and drying done on a field or if it was continuously flooded, a full range of weather conditions in terms of drought summers, hot summers versus more mild ones. And so we can really start to put the sort of impact of drying and different irrigation strategies on the carbon balance of these fields. And so really starting to look at over a 10-year time period, is this field a net carbon source? Is it a sink? And how does that respond to management? So.
Well, Will, thank you. I want to thank Dr. Runkle and Will for being here today. They traveled down from Fayetteville to be in studio for this. They've got a lot of great information, and I just really appreciate their dedication and the responsibility they take in trying to help our rice farmers be sustainable. Make sure you be on the lookout for emails and advertisement about our next segment, which will be on water conservation and blackberries. I think we all love blackberry cobbler, so we want to make sure you tune in and find out how we're conserving water and those things. With that, we'll sign off today, and we thank you so much for your being willingness to and wanting to attend these webinars. Thank you so much.
Thank you.
Thanks.
Thank you for joining us for the Soil and Water Conservation Virtual Field Trip. This broadcast is funded by NRCS and produced by the University of Arkansas System Division of Agriculture Cooperative Extension Service.